All right, let's see. Check our stream ahead of time. Hello, come sign in. Got some cookies and candy if you want. All right, so let's test our stream. Testing. 1, 2, 3, 10. You guys hear that? Can you guys hear me? I'm just kidding. Of course you can hear me, right? Of course, but can we hear this, right? Is it live or is it Memorex? You guys know that commercial? Live or Memorex? Okay. All right, let's see. I'm gonna go to Canvas, see if this works. Announcements. Can you hear it? Hello? Can you hear it? Hello? We do this every time. We have not started. We're just chatting. We do this every time. We have not started. We're just chatting. Okay. It works. Echo. Okay, cool. Infinity. Huh? I have, I'm sure I don't have any viewers. I don't have any viewers, no, zero out of, oh, wait, somebody just joined. Hola. Hey, Liz, how you doing? Okay, so, yeah, let's put up our, anyways, anybody have questions? Everybody sign in? You got questions? Anybody have questions already? So we will go over the study guide. It's not gonna take 2 hours. And then I will go over the 10 advanced questions. And if you have any questions at that time, that would be the time to ask. Hello. Come and sign in and grab some cookies and candy if you want. No obligation, but please do. So 8 a.m. is on the right, 9:35 is on the left. Hello. How you doing? Good to see you. Hello. You're on the screen now. Live stream. I started it early today. We'll actually start on time. Anybody want some Kleenex? I got Kleenex up here. Yeah, you want some? I will. You will, okay. Are you getting over something? Are you feeling better? Yeah. Good. I know, actually, I feel so bad. I hope I didn't get anybody sick. Nah, but I mean, there's lots of other sick people around. Yeah, exactly. All right, we're just sipping our coffee, waiting for a few more minutes. Let me think, anything entertaining. I'm gonna head to Texas for the break. All right, let's get that centered. I wonder if I can zoom in on that. Can you guys read it? Looks like it's pretty okay. Can you read it okay, Liz? Aw, you're okay. You're here in spirit, Liz. Oh, look, we got 2 viewers. 3. We got 3. Woo! That's the highest number I've ever had. No, I've got 5. Oh my gosh. Hey, how are you, Jacob? Come and sign in and then grab some candy, cookies if you want. Good, good. How about you? All right, you guys. This is going to be the best test ever, right? But you do want to, like little bits of advice. If you haven't already gone to look over your old exams, it's probably going to help if you do that, right? To at least figure out which questions you didn't get right, because some of those are going to show up on the final, right? So, hello, come sign in, grab some cookies and candy, and you're going to walk in front of the stream. Everyone will see you on YouTube. Hey, YouTube. Say hi, YouTube. Sorry. Yeah. Just wave. We're just all informal right now. We're just chilling. You got your blenders. I got my coffee right here. Yeah, cheers. Cheers. 8 o'clock is on the right and 9:35 is on the left. Are you okay? Oh, no. What happened? Okay, no problem. No worries. No, don't worry. It's no big deal. Yeah, don't worry. I do it all the time. Nobody panic. It's okay. Don't worry about it. It's our last day using this. Luckily, it's the final exam. No more exams after this. Oh my gosh, is anybody excited about that? I'm going to miss you guys too. Actually, you guys have been a really good class. I wish, yeah, just do the final exam column. That's it. Yep, final exam. Hello, come on in. Sign in over here and then grab some cookies. You're going to be walking in front of the live stream. You are live. Sorry. No, we didn't start. We got a couple of minutes. Grab a Kleenex if you want Kleenex. Anybody need Kleenex right now? Okay, like I said, this is going to be actually the shortest review yet because we only have 2 chapters to cover. So the good news is we can easily cover it. There's no bad news. Actually, there's no bad news. I mean, if you have questions, we can stay. I have 2 hours booked here. So anything you want to ask questions on, we can review concepts from before. But the focus today is primarily the 2 chapters. And then I will go over at the end the 10 advanced questions. If you didn't go to the tutors, you will get them right now. All of you at home, if you didn't make it to the tutors, you've got a chance. Caleb, hey, how you doing? Sign in. Walk in front of the live stream. Say hi, YouTube. Hi, YouTube. Hey. Oh, we're up to 7. Woo! That is a record right there. 7 people are streaming our channel right now. All right. Does anybody have questions before we start? Anybody like something confusing? Anything confusing? Anybody interested? So, by the way, this session was sponsored by Sean Kelly, and Sean Kelly teaches this amazing course. I just really want to recommend it to all you YouTubers out there. Come on over here. Come on, sign in, and grab some cookies and candy if you want. You're all good. You're on time. You're good. But there's a course called Introductory Astrophysics. It's really not made for most students, but a few of you out there like math and maybe want to try doing math with astronomy and physics, and it's a really fun course. So I haven't been able to teach it in a while because I don't get enough students. I'm just going to keep advertising it. Yeah. But during this class, we did basic physics, and I take physics before, and I was starting to get bored of the column. So next semester, I split, and I'm going to be doing physics. No, you're not. Are you kidding me? You got to come talk to me. Yeah. Cool. Come talk to me. That's awesome. Wow, I'm so excited. You like physics, huh? Physics is amazing. And astrophysics is awesome too. Come sign in, grab some cookies, and we're about to begin. I guess we're going to start on time for once because I actually set up early. Also, they said, yes, this is 8 o'clock over here, and that's 9:35. Yeah. They did say they would open the bathrooms. I'm going to actually go see if I can get in the bathroom right now. On streaming live on YouTube. Oh, yeah. The bathrooms are open. Woo. Boy. Hello, come sign in. The bathrooms are open. We have bathrooms. Yay. How you doing? Sign in, and then the bathrooms over there are open, the men and ladies' room. Hello, how you doing? Say hi to YouTube. You just went past it. That's cool. Okay. So sign in, 8 o'clock here, 9:35 there. Cookies, grab your cookies. Come on, lemon cookies. I brought a whole new pack of lemon cookies for all you lemon cookie fans. Lemon cookies, I got plain and whatever kind in there. Half and half. I got Starburst. Okay, if you guys are ready, we're ready to get started. Are you ready? We're gonna have more people. Let's see. Ooh, we're up to 7 still. Okay, that's cool. What do you need? Anything? Pencil? Go for it. Yeah. No problem. No problem. Hey, Dylan, how you doing? Go ahead, sign in, and then grab some cookies if you want. All right, I'm glad you guys could be here today. This will be our shortest review ever because it's only 2 chapters. Sorry, go ahead. So we'll stay focused, and if you have questions at the end, we're gonna after we cover the 2 chapters, we'll cover the 10 preview questions, and then if you have any questions, I'm happy to stay as long as you like. No, not as long as you like. I will stay until 5 o'clock, and then I'm gonna go meet my wife. We're gonna go watch. There's a parade of lights in the harbor. You guys gonna go see that? Just chill for a few minutes and watch the boats with their lights on. It'll be fun. I think there's even fireworks, maybe. I don't know. I'm not sure. Not sure. No guarantee. Fireworks too. You gonna go? Yeah. I haven't gone in a couple years, but yeah, I'm gonna go tonight. Check it out. I need a little relaxing time. Hey, come on in. Sign in. Grab some cookies. Wave to YouTube as you come by. Come on. Right over here. 8 and 9:35 is the far one. Okay, you're live on YouTube. Check it out. Find yourself. Actually, do you guys want to be on YouTube? Raise your hand. I want to be on YouTube. Okay. Actually, I don't have permission, though. Here's everybody. Say hi, everybody. Everybody wave to the at-home audience. Okay, here we go. I've never done that. All right. I like doing new things. Okay. All right. Sorry you guys couldn't be here with us, but, you're with us in spirit. All right, we got a little bit of work to do. It's not that bad. We are ready. We're already set up. The stream is live. We got our cookies. If you haven't gotten cookies, there's cookies. Go grab as many as you want until they're gone, and then I have nothing left. That's it. But if you eat them, then I won't eat them, and I really like them. So it's kind of important that you just eat them. All right, so if you guys are ready, let's go ahead and get started. We are starting with chapter 15. Okay, this is our Milky Way galaxy. Okay. So we'll go through the terms, and then we'll probably elaborate a little bit. But the key thing is down at the bottom, right? You want to know the little things because there's questions related to not just the terms, but maybe these connections down here. All right, so starting with number 1, what is a galactic fountain? Anybody remember galactic fountain? The idea was a galactic fountain is material is blown away from the Milky Way, and what force brings it back to the Milky Way? The force of gravity, but it comes back in a different place. And so imagine material streaming from one part of the Milky Way to another. It solved the problem that Lyman Spitzer had no answer to. How does the Milky Way get so mixed up? It's really well mixed. It's almost the same in any direction that we look. And the answer was Bob Benjamin's article on the galactic fountain. So galactic fountain, we blow away material from the disk using a supernova. And the way we see it is coronal gases. And then that material falls back to the disk under the influence of gravity. So it allowed the material to be mixed. What is the Milky Way? Come sign in down here and grab some cookies while you're doing it. And then have a seat. Okay, the Milky Way is a galaxy. You're supposed to know a few facts about it. They're listed at the bottom. But maybe we can just run through them real quickly, actually. Let's run through them. Let's draw a quick little diagram of the Milky Way. This will have all the parts on it, too. Right? So here we are with our whiteboard. This is the new technology side. And so the Milky Way is what kind of a galaxy? A barred spiral. But if you said spiral, you're almost there. But it's called a barred spiral. And it has the main disk, right? The main disk, what is the dimension of the disk? There's a couple of numbers you're supposed to know. So 100,000 light years, or how many kiloparsecs would that be? That's 30 kiloparsecs, okay? So from one side of the Milky Way to another, the diameter of the disk. Sharon, come and sign in and grab some cookies if you want, okay? So that's the size of the disk. And then in the center of the disk, we have a bulge, right? The bulge is a circular, a spherical-sized object, right? And it has a diameter of about, how many light years? Anybody remember that? I don't know if we did light years. We did 10 kiloparsecs across. Yeah, how about that? How many light years would that be? I don't know if we need to know that. I can't think of it right now. How many light years? 3.26. 1/3. Oh, it's like 33,000. There you go. Like 1/3 of 100,000. How about that? 33,000 light years. Okay, I like 10 kiloparsecs. This is a pretty good one. Okay, then we have a halo. What does the halo look like? The halo is the spherical shell that goes around the entire Milky Way, where we find the globular clusters whizzing around in every different direction. Yeah. This is called the bulge. Sorry, the bulge. Okay. Okay, so we have the disk. Go ahead, I'll write it down. Disk in the middle, the bulge. Then we have this orange outline, which I can't see very well, so you guys probably can't see it either. It's called the halo. And that's it, right? The disk, the bulge, and halo. How big is the halo? The same dimension as the disk, right? About 30 kiloparsecs. Danya, don't forget to sign in and grab some cookies if you want. Okay, all right. And anything else? What do we find? There's too many other questions. We'll get back to this, right? So that's those are the dimensions that you're supposed to memorize. The main disk size, the halo size, and the bulge size. And then we'll talk a little bit more about what we find in those different locations, right? Okay, so Carolyn and William Herschel, the Herschel siblings. What do we remember about those two? William was a telescope builder, and his sister helped him to do what? They mapped the Milky Way. They looked up at the sky, and by hand, they plotted out the location of the stars. They were really careful, and they managed to see that the Milky Way is a big disk of stars. But it was really too small, and where was the sun? Where is our sun? At the center, right? And so that wasn't right. We know that's not correct, but it's what they figured out. It was the very early time, the end of the 1700s, beginning of 1800. A little bit later, later in the 1800s, we have Jacobus Captain. He came up with a better technique for finding the location. Come sign in and grab some cookies. And what was his better technique for locating the stars and drawing the disk of the Milky Way? He took pictures, a photograph, and from the photographic plate, he plotted very carefully the positions of the stars, and he saw that there was a disk about 10 kiloparsecs across, about 2 kiloparsecs high, but that was again too small. And where was the sun? In the center. So both of these techniques relied on counting stars, right? Plotting the positions of the stars. What was wrong with those two techniques, or the same technique? What's wrong with it? You can't see all the stars, right? The dust blocks your view. So you can't see all the stars, and so what you see, as many as you can see, come sign in, grab some cookies, and you see us being in the center because you can't see the whole distribution. Okay, finally, we get to, we get to the globular clusters and Harlow Shapley. Harlow Shapley studied the globular clusters. You're supposed to know, how many does the Milky Way have? 150, right? It's a small number. Oh, I forgot to mention, how many stars are there in the Milky Way? About how many? Actually, this is a question on your final. Not the exact number, but the order of magnitude. I'm giving it away because you guys are here. I feel kind. What is the number of stars in the Milky Way? I'm going to write it down for you, and you're going to, yes, you know. 4 billion or a little bit more? I think it's a little bit more. Anybody know the real number? You're close, though. You got the right billion, and you got the number 4, but you forgot 2 more zeros. It's 400 billion. So the number of stars in the Milky Way, the stars in the Milky Way is 400 billion. Okay, so I don't know about you, but I haven't done scientific notation in a while. Maybe I should just do a quick refresher. Okay, so 400 is 4 times 10 to the second. And what is a billion? Does anybody know what power of 10 a billion is? 10 to the ninth. Very good. So times 10 to the ninth, which gives me 4 times 10 to the 11th stars, right? That's the number of stars in the Milky Way. What's the order of magnitude? Does anybody remember order of magnitude? It was way back in chapter 1. 10 to the 11th. Because it's a 4, which is less than 5, we just say it's of order of magnitude 10 to the 11th stars, which, by the way, is the same as the mass. If you remember, the mass of the Milky Way is about 10 to the 11th solar masses. So it's about the same as the number of stars that we see in the Milky Way. All right, anyways, I just gave away a question. You guys are here, you're paying attention. Give it away. Actually, I'm giving them all away by doing this review. They're all in here, right? Well, at least all the new questions. Hello, come sign in and grab some cookies while you're here and wave to the audience at home. No, just come on. Okay, just walk around like this. That's okay. I'm sorry. You didn't want to say hi. Okay. Hey, we're up to 9. I've never had this many simultaneous viewers. All right, anyways. Okay. So what did Harlow Shapley, when he looked at the globular cluster, what's a globular cluster? Maybe we should remind ourselves. What is that? A nice spherical cluster of old or young? Old stars. They've been around maybe even longer than the Milky Way. They're made of old stars, several thousand stars. What is the force of gravity enough to keep them together? Yes, that's why they're still here after 13 billion years. So they stay together because there's a lot of stars and they form a spherical shape. So they look like a dandelion or something. And there's 150 of them whizzing around in every different direction around the Milky Way. When Harlow Shapley studied those, they are above and below the disk mostly. They are not obscured by the dust. And he found a spherical distribution and he said, the center of the Milky Way is the center of that. Is that where our sun is? It is not. And so he finally did it right? He finally saw that we are not at the center of that distribution. How far away are we from the center? Another little number you're supposed to know. 8 kiloparsecs from the center. So if the radius is 15 kiloparsecs, we're a little more than halfway to the edge, a little more. Okay. All right. So the galactic disk is the main structure, right? Where is most of the mass? Actually, that's not true anymore. Oops. Where are most of the stars? How about that? That's true. Where are most of the stars? In the disk. There's more stars in the disk. Where are all the new stars? In the disk, right? All the new stars are in the disk. What about the bulge? Actually, there are a few new stars there too. But the bulge is that concentration in the center. And there are a lot of older stars that are very densely packed, if you remember. And then in the halo, we have the globular clusters that we can see, okay? So we are a spiral galaxy, a barred spiral. A spiral galaxy has arms. And are the arms full of stars? Actually, not quite, right? The arms that we see have stars on the edges of the arms, and the interior parts of the arms are still raw material that will one day form stars. So we can actually see the formation of an arm is going to be a lot more stars in the future. It just hasn't formed yet. Okay, there's a concept called metallicity. What is metallicity? The generation of the stars, right? Each generation enriches the next generation. So the first generation stars had just about all what elements? First generation. Hydrogen and helium, that was it, right? The raw material was hydrogen and helium. But as each generation lives and dies, it seeds the next generation with heavier elements. And so they get enriched with things that are above helium. And that's what we call metallicity. Okay, so we think that our sun is probably, what did we say? A third or probably fourth generation star. Okay, population 1 stars, the ones that are closest to the Earth are found where? In the disk. They're in the disk. They're nearby. Hey, come on over here. Come sign in. See if he'll walk in front of the screen. No, it's okay. I was actually thinking it would be kind of fun. Could wave to the people at home. You know. And then grab some. Oh my God, who brought the cake? What the heck? Who brought that? Oh, you. That's so sweet. Oh, That's so cute. Is that for my birthday? Did you know it was my birthday yesterday? Oh, it was my birthday. Okay. Yeah. I got a nice cake. Yay. You guys are funny. Okay, population 1. The stars are found in the disk of the Milky Way, right? Are they young or are they old? They tend to be younger or older. Which one? They tend to be younger stars, right? More of the younger stars are in the disk. And are they higher or lower metallicity? They're higher metallicity because they're younger, right? They were born after other stars died. Population 2 are a little bit further away. They are in the halo, right? That's where the globular clusters are. Are they young or are they old? They're older stars, right? And so do they have high or low metallicity? Low metallicity because they're really kind of old stars. So they've been here as long as we've been around. A barred spiral galaxy, that's what the Milky Way technically is. A barred spiral is a spiral that has a stretched out center. So maybe we should just look at a picture instead of talking so much. I actually have that luxury because today it's just 2 chapters. But if I just waste time, I could probably make it go. But I won't do that. I'm very focused today. A barred spiral galaxy. Okay. So a barred spiral has an elongated center instead of a single center, right? So it's stretched out. And we talked about why it would be stretched out. What would cause a galaxy to be stretched out like that? Okay, you should be saying another galaxy passing by, exerting what kind of a force? A tidal force. Tidal force is a stretching force. So somebody flew past a pretty massive galaxy, didn't stick around probably, just kept going, but stretched the Milky Way in the process of flying past with the gravitational tidal force. Okay, that sounds good. I like it. Actually, your book doesn't really say it so easily, but I really think that's the answer. Okay. All right. Our local group is the group of galaxies that is close by, and they are all gravitationally bound. So they will be with us until when? How long will they be with us? Forever, right? Even though the universe is expanding and everybody else is going to leave us, the local group is going to stick together and be together forever, okay? So when the whole universe goes dark, we will still be able to see a few galaxies, the nearby galaxies. One of those galaxies is called the Andromeda Galaxy. What's special about it? What kind of a galaxy is it? A spiral galaxy. It has about 1 trillion stars. I don't think you have to memorize that, but you should know that it's a spiral galaxy. And something else you should know. It is on the way, right? It is on its way, and we're going to collide with it. In about between 4 and 8 billion years, there's going to be a merger. And when we're done, there will be a single galaxy. What's the name of that single galaxy called? The Milky Galaxy. Milky. That's on your final. So make sure you know that name. Milky. Here's another bonus for next chapter. Does anybody remember what kind of galaxy it will eventually become? The Milky Galaxy, after it settles down over time, it will be an elliptical galaxy eventually. It may be a while before that happens, but eventually it will be. Okay, large and small Magellanic Clouds. What are those all about? Those are little dwarf galaxies that are orbiting the Milky Way, and they're called satellite galaxies. They're a little bit too close. What do I mean by that? We are ripping them apart. The Milky Way's tidal force is ripping them apart. And we can see streams of matter that are being dumped onto the Milky Way as a result of that. Okay, so again, I could probably show you that. Should I try? Let's see. So there's a large Magellanic stream. Oh, I misspelled it. Okay, Magellanic stream. The Magellanic stream. Okay, so we see streams of matter dumping on. This is actually pretty cool. Okay, so you can actually see streams of matter being ripped off of the large and small Magellanic Cloud that are ending up being dumped on the Milky Way, right? Again, what force is causing this? The tidal force, right? The tidal force. Actually, the force, Luke. No, Just kidding. All right. That was a joke. Sorry. Bad joke. All right. Stay focused. Okay, so large and small Magellan Cloud are a couple of dwarf galaxies. Anybody remember the masses of them? They're roughly the same, a little bit more, a little bit less than the Milky Way. A lot less, actually, like 1/10, and then a little less than 1/10, and they're much smaller too. So I think large was about 4 light years, 4 kiloparsecs across versus 30 for the Milky Way. And then the small was only 2 kiloparsecs. So they're really tiny little galaxies. So we understand why they're being ripped apart and not the Milky Way being ripped apart. Does that make sense? Okay. All right, spiral density. Sorry, we got to go back. O and B associations are related to what? Detecting what part of the Milky Way? What are we thinking about? The spiral arms. How do we see spiral arms? It's going to come down here in a few minutes, but what we see is actually there's 2 mechanisms we can see the spiral arms. One is an indirect and one is a direct. Come get some cookies and sign in, get your extra credit. Okay, so indirect, we see on the edges of the spiral arms, we see these big, hot, young stars, the O and the B class stars. You guys remember O, B, A, fine, girl or guy or giraffe, kiss me, right? What does O and B mean? The hottest stars, right? The hottest, most massive stars. These are on the edges of the spiral arm. And so they're showing us where the edge of the spiral arm is. Is there a direct mechanism for seeing the cool, high-density interstellar medium that's in between those O and B associations? Is there a direct mechanism for seeing the neutral hydrogen gases that are in between the O and B associations? Can we see them? And the answer is yes, we can now, right? What technique do we use? The 21 centimeter radio waves. That's what you want to think about. We can directly see the hydrogen through absorption and, according to the author, emission. I think absorption is more important, but I'll go ahead and say absorption or emission of 21 centimeter radio waves. That's a really special one. Okay, spiral density wave, I left it in there, but really don't worry too much about it. It just means that the stars form in waves that gradually descend down the length of the arm. And as a result of this, you can see that there are not stars the whole way along the arm. Sometimes you have gaps. So depending on how the spiral density wave is working, I wouldn't worry about that one too much. Sagittarius A star, we're missing a star right there. What is that? You definitely need to know about that. Supermassive black hole at the center of the Milky Way. It's in the direction of the constellation Sagittarius. And you may also want to know the mass of it, just because it's kind of a neat thing. It's 4 million times the mass of the sun. And how do we know that it's there? Have we actually seen it? We can't really see it most of the time. It's quiet. But we do see, stars orbiting something invisible. And so that little video clip of the
Isn't it like weird sounds or something?
well, they actually it did a flash last year of gamma ray burst, but it's still a little bit up in the air what caused it. We don't quite know. Let me put Sagittarius A star, and then the ESO made a nice video. Okay, zooming into, we'll just watch this for a second, okay? Zoom in, watch it on. Everybody at home, we're reviewing, we're just watching something that you saw before for 1 minute, because it's cool. We're zooming in, zooming. Oh, it's gonna, I think I got the glitchy video. Maybe not. Okay, we're looking at an infrared image here, and you can see that these stars are orbiting something that's not even there, right? Something invisible. And when we calculate the mass of it to be able to whip that star around like that, that's where we get the 4 million times the mass of the sun. Okay, so that one actually is called S2. I think it takes about 16 years to make one orbit. So we've seen it do a full orbit, actually even more than a full orbit. It's a black hole, supermassive black hole. So this is going to come up in the next chapter, but how do we even see a black hole? Can we see a black hole, and why not? Why can't we see a black hole? Who knows the reason why we can't see a black hole? Because light can't escape from it, right? Once light gets too close to a black hole, it can't escape, right? The escape velocity of the event horizon is the speed of light. So once light gets in that inside that radius, it can't ever get out. But we can see material that gets sucked into a black hole. A star comes too close and is ripped apart. It will go into orbit for a little while in a region right next to the black hole called the accretion disk, right? And so we see that, right? So the picture last year of the first picture of a black hole was actually of the accretion disk. And those get so hot, like 1,000,000 Kelvin, that they glow in the X-ray part of the spectrum. So we can actually see them with an X-ray camera. And we do see them. There's a number of them all over the place. So last year, X-rays and even higher energy. Last year, Milky Way did have a brief burst of a gamma ray burst. We think that it just ate something. Okay, so as long as it's not eating, it's black, right? You can't see anything. But as soon as it's feeding on something, for a little while, you'll be able to see it because of that accretion disk. All right, here we go. Jumping forward to Vera Rubin. Why is she important? You need to know her name. Her name is on the final exam. You need to know her name. She was the one who discovered the existence of dark matter. Now, we actually don't know for sure that dark matter is real, but we like the theory of gravity. It could be, so here's the option. We keep the theory of gravity, but we have to come up with this material that exerts a pull of gravity to keep stars from flying away from the galaxy. Or the theory of gravity is wrong. Einstein's theory of gravity, which we really like a lot, right? Which has been one of the most successful theories to date that human beings have ever created. Okay, so either way, we got to learn something, one way or the other. What is dark matter? We do have a few ideas. Neutrinos are part of the story, antineutrinos too, but that's a small fraction. We cannot actually explain what it is. But Vera Rubin looked at the rotation curve of galaxies, right? Rotation curves of galaxies, which is how fast are the stars moving the further away you get from the center. And what should have happened was that as you get further away from the center, the stars should have slowed down. I actually think now would be a good time for me to bring up that slide because it's on the final exam. So this slide is on the final exam. This picture is on the final exam, which means you really need to understand it, right? What does this picture mean? Okay, let's talk about what it means. I can give you all the answers. All the answers right here. There it is. This slide, this picture is on your final. What does it mean? So when we looked at a galaxy rotation, we noticed that the stars that are further from the center of the galaxy don't go slower. They should have gone slower. The blue curve is what we expected. What is the blue curve modeled on? What is it kind of based on? The solar system gravity, right? We know that the sun is the core of the solar system. That's where the strength of gravity is coming from, that big ball of mass in the middle. So the further you get from the sun, the weaker the force of gravity is. So the further away, the weaker, which means that the planets have to move slower in their orbit. So the further away you get from the sun, the slower the planets go. That blue curve is what happens in our solar system. We thought that the galaxy would be the same way. Were we correct? And Vera Rubin said, not at all. We were not right. We were incorrect. So the model that we had for the distribution of matter was wrong. Okay, it is not concentrated in the middle and get weaker as you get further away. Gravity does not seem to get that much weaker. So what happens? Well, there must be more matter there than we can see. Something is causing gravity to be pulled on the stars. They're not flying away from the Milky Way. They're staying here. They're not flying away from other galaxies either. So the answer is dark matter. So actually, maybe we could find a picture of a dark matter halo. Oh, do I have one in here? Well, that's important. You should need to know the amount of dark matter, unfortunately, is 90% of the matter in the galaxy is dark and 10% is luminous. What does the word luminous mean? Shines with light. So it's lit up, it's stars, right? Things that we can see. Non-luminous or dark means we cannot see it. It does not interact through the electromagnetic force, right? We cannot see it. So it may interact through other forces. How many forces do we have? We have 4 altogether. We know that it interacts through gravity, though. Okay, so the dark matter halo is a spherical distribution, and according to this picture, it's even bigger than the halo for the Milky Way, and that's where 90% of the galaxy's mass is located, all throughout, not just outside, by the way. The whole sphere of that area is full of dark matter, which means we have dark matter going through us right now. We already knew about the neutrinos, but there's probably a lot more. Neutrinos are just a small piece of that. So there's this stuff that goes through us and doesn't interact with us in any way. How do we even know it's there, right? It's invisible. We can't see it, except it exerts a force of gravity. And so anyways, that's our dark matter. And yeah, anyway, so a couple theories on dark matter that you're supposed to know about. One was the Macho Theory. The Macho Theory was massive, compact halo objects, right? And what was a really great candidate for Macho particles or Macho objects? What was it? Black holes, right? It would have been a whole bunch of black holes. I was a really big fan of that for a while. And then it turns out they did an experiment in which they showed that was not possible. What was the experiment that they did? What were they expecting to see? Because the black holes are whizzing around, you would be able to see this. Supposed to know the name of this. So what happened? The light would bend around the black hole and you would see all of the light at once. It would be a flash of light called a micro-lensing event. Every time a black hole went inside of a star or a galaxy, you would see all of the light concentrated at once in a burst of light. And so they should be all over the place. You should see flashes every time you look at the sky, but we don't. We see them just once in a while. So there are some black holes, but not very many, much, much less than we need. So machos are out. We think machos are not real because there's very few micro-lensing events. Micro-lensing. Do I need to draw that? Anybody need help? Micro-lensing. The black hole bends the light around it. You get a flash of light all at once. So it kind of like concentrates the light, micro-lensing event. So we're left with another alternative called WIMPs. What does WIMP stand for? You need to know what it stands for. Weakly interacting massive particle, right? We need to be massive, first of all, to exert a force of gravity, but the weakly is a little clue to the other force that it would interact with. What do we think that it might be? The weak nuclear force. So we think that the strong nuclear force, if these particles interacted through the strong nuclear force, it's a really big part of how atoms are held together. We think we would have seen it already. It would have been more obvious. But because we don't see anything like that, in other words, it would cause atoms to mutate, to transmutate, right? To break apart. If it was interacting through the strong nuclear force, it would affect nuclear decay. But we don't see anything like that. Okay, so we think that it doesn't interact through the strong nuclear force. It's got to be the weak nuclear force. But it's possible that it doesn't even interact through that, in which case we can learn nothing until there's another force which we don't know about. So basically, we're hoping that the weak nuclear force is the other avenue by which we can feel these particles. Otherwise, we're in trouble. But we have a guess that it's going to be right. So weak nuclear force and gravity are the two forces that WIMPs would interact with the rest of the universe. Okay, let's go through. Actually, I've talked about a lot of this, but we'll just talk again. Describe Bob Benjamin's interaction with Lyman Spitzer. So Bob Benjamin was a graduate student, wrote his article, sent it in, and I talked to you guys a little bit about the whole peer review process. Lyman Spitzer was one of the referees who read the article and gave feedback and was actually super excited, ended up working with Bob for many years after that. but it explained a problem that no one had a solution to, is how does the Milky Way get so well mixed? And in this, he described a mechanism by which supernova blasts material away from the Milky Way, and then it falls in under the influence of gravity. And so it's a fountain of material that goes from one part of the Milky Way to another. Okay, so how has the model of the Milky Way changed in the last 250 years? So we have the Herschel siblings, did a star count, right? Star distribution map. The solar system was in the middle. We had Jacobus Captain, did photographic plates, but again, counted stars, and the distribution was, solar system was in the middle. And then finally, we got Harlow Shapley, who looked above and below the disk at the globular clusters, no longer obscured by the interstellar dust in the Milky Way. He could see that the globular clusters have a distribution with the center not where our sun is. Okay, so that was that's what I'm looking for. Everybody good? That's it. Okay, so we know that the Milky Way is about 100,000 light years across, 30 kiloparsecs, and our solar system is 8 kiloparsecs from the center. All right, explain how the Milky Way center, I just did that, right? So why did the globular clusters work when stars didn't? They were not obscured by the dust. Okay, they were not obscured by the dust. Okay, clearly describe the differences between a population 1 and population 2 stars and where they are found in the Milky Way. Population 1, what do you say? Young, hot stars found in the disk, right there. That's pretty much everything you need to know. Come sign in and grab some cookies. Okay, young hot stars found in the disk, population 1. Population 2, older, cooler stars, right? Redder stars that are found in the halo, okay? Often in globular clusters, right? Okay, pretty much most of them. All right, describe the interactions among the galaxies in the local group. In particular, the effect on the Magellanic Clouds. Okay, so I've kind of described all of this for you, but let's go through it one more time. Describe the interaction. So what force keeps the galaxies together in the local group? It's gravity. Again, gravity, right? Gravity is strong enough to keep all of these galaxies together. And the Magellanic Clouds are too close. They're satellite dwarf galaxies that are getting ripped apart by the tidal force from the Milky Way. So the Magellanic Stream is that material being ripped off and feeding the Milky Way. Okay, the Milky Way is going to collide with the Andromeda Galaxy. And that's about 8 billion years from now. We'll be merged together with it. No longer Milky Way, no longer Andromeda. How many stars do we think are going to smash into each other during this collision? None, right? We think the space is too big. And so they're just going to merge together to form one big elliptical galaxy eventually, right? Elliptical galaxy eventually. Okay, explain how we see the spiral arms, okay? Direct and indirect. I kind of did everything already. You guys remember? So what's the indirect evidence for spiral arms? The edges of the spiral arms, what outlines them? These young, hot O and B stars, that's called an O and B association. How do you directly see the material in the middle of the arm? The cold, dense hydrogen gas, neutral hydrogen gas. How do you see it? 21 centimeter radio waves, right? Absorption and emission. That's how you directly see that material. And we see this in other galaxies too, not just in the Milky Way. Okay, so explain how Vera Rubin deduced the existence of dark matter. She looked at the rotation curves and she said, those stars out here at the edge of the galaxy should be flying away, but they're not. And therefore something is keeping them there. There's more gravity than I can see with the stars that are present. There must be dark matter. Okay, machos could be detected. We already did that. What was the answer? How do you detect machos? Micro lensing, right? A flash of light comes around, the light comes around the black hole. We get a big flash all of a sudden. We would see those all the time. We don't see them. Why are WIMPs so hard to detect? They only interact through gravity and the weak nuclear force. It's really weak, right? And very, very confined. And so we just don't have the technology quite yet. Maybe we will advance in the next few years. We'll be able to detect them. Hopefully they interact with, we know they interact with gravity, but we hope that they will interact with the weak nuclear force. That's about it. There's only 4 forces that we know about: gravity, electromagnetic, strong nuclear force, and weak nuclear force. That's it. So if we already said they don't interact with light, right, electromagnetic, and they probably don't interact with the strong nuclear force because we would have detected. Then there's only those last two. Okay. How is galaxy formation similar to solar system formation? Can anybody tell me one thing that's similar? Galaxy, solar system. What's similar? What's the shape? Is that similar or no? You get a disk. How about that? Is that pretty similar? Yes. Okay. What gives you the disk? Conservation of angular momentum, right? So something that is rotating, when it collapses, rotates faster and flattens into the shape of a disk. Conservation of angular momentum. It's true whether you're a galaxy or a solar system. So what's different? Is matter distributed the same way? No, we discovered that that's not the same, right? So that would be a dramatically different. In a solar system, where's the matter? In the sun, right? In our solar system, what fraction of the solar system is in the sun? 99, anybody remember? 0.86. So like 99.9% is in the sun, and everything else is just a little tiny bit that's in the disk around the sun, right? And then in a galaxy, it's really not true. 90% of the matter is in the halo around the galaxy, and 10% is in the disk and the bulge. I mean, it just doesn't work. It's very different. In fact, it's so different, I can tell you I don't get it. I mean, it's really bad. I'm really embarrassed, in fact, to talk about this. It's really, I have to talk about my invisible friend, dark matter, you know. He's right next to me, I promise. But anyway, okay, so memorize. We got a few memorized things. We've gone over these. Oh, I forgot one, though. Thank God I put that. Thank goodness I made this, right? The thickness, I forgot the thickness, right? The disk thickness is 0.6 kiloparsecs, 2,000 light years. And then I think I got the rest of them. Another one, so the name, you don't have to know the Orion arm. Some people say Orion, other people say Orion Cygnus, depending on who you talk to. But we're 8 kiloparsecs from the center. You definitely need to know that. And then the sun orbits the Milky Way on a circle, about 233 million years to go once around. Now, does the sun orbit in the same plane that whole 233 million years? This is not on the study guide, but does anybody remember? Do you remember that it could be a little bit above or below the plane? And so gravity pulls it down, and then it overshoots, and then pulls it back up and overshoots. It actually oscillates a little bit above and below. That's just a tiny little detail, just because it's cool. No other reason. It's not on your test. It's cool. All right, the mass of Sagittarius A, 4 million. Solar masses, and then dark matter is 90% of the Milky Way. Okay, that is chapter 15. Everybody good? Look at this. 44 minutes. How could that be? Oh my goodness. Okay, here we go. Chapter 16. Okay, let me take a sip of coffee. Anybody? Oh, I want to eat a piece of cake. Can I eat a piece of cake now? Oh my God, that's such a beautiful cake. That was a pretty cake. That was so sweet. All right, here we go. So chapter 16 is talking about the great debate, right? That's what this chapter is all about, the great debate. What's the great debate? Anybody remember? The great debate. We had a debate, right? The nature of the universe. What is the universe? And in particular, the way we wanted to ask the question is, what was the spiral nebula? What are these spiral nebulae? What are they? Are they within the Milky Way? Are they part of the Milky Way? Or are they whole, separate galaxies? And we're just one of the galaxies. And that turns out to be the right answer. But, okay. Question? Comment? Okay, everybody good? Are you guys passing notes around? Okay. All right. So spiral nebula. Give me an example of a spiral nebula. Anybody? A very famous one. This was the spiral nebula, 1925, 1930. It was called the spiral nebula. The great spiral nebula of Andromeda would be an example of one, right? They were spiral galaxies, but we didn't know that at the time. The word galaxy was just for the Milky Way. Okay, galaxias. So the spiral nebulas will become spiral galaxies. But up until this point, we don't know. Are they, like planetary nebulas? Are they disks around a star? Maybe they're around a star. Maybe they're swirling around. In fact, some people thought that they measured them moving. And were they actually measuring them moving? What do you think? Remember I said it takes 233 million years for the sun to go once around. Do you think they were measuring the movement of a galaxy? No, that is not going to happen. It's not fast. It's incredibly slow. Human beings do not live long enough to see galaxies rotate, right? We just don't live long enough. So no, they could not. All right, so grand design spiral was an example of a beautiful spiral. What is special about a grand design spiral? Actually, I can bring up the slides. How about that? Anybody remember? You can see the arms from the center to the edge, okay? You can see the arms from the center to the edge. That's a grand design spiral. All right, here we go. Grand design spiral. There we go. There we go. Grand design spiral. So grand design spiral, you can see the arms, they're well defined from the center to the edge. Actually, it's not a big deal. I don't know why I'm even bothering, just to look at something. A flocculent spiral has a little patchy look to it. So as you go along the arm, you'll see gaps. It'll be dark patches. So flocculent spiral is not stars all the way from the center to the edge. A barred spiral has an elongated center. Bars formation. Elliptical galaxies. What's an elliptical galaxy look like? An oval shape. It can be spherical too, by the way. In fact, Hubble gave them numbers, right? So there's E0 would be a perfectly spherical galaxy, and then more stretched out would have a higher number, right? So E1, E2, E3, they would be more stretched out, more elongated. So they're egg shape or football shape, okay? So actually, let's go back to our study guide. Okay, so elliptical galaxy, irregular. What's an irregular galaxy? You don't have to know about CDs. Don't worry about CDs. Irregular? Yeah, it's actually galaxies colliding. So they don't look like anything. They're a big mess. And that's why they're in the process of colliding. So irregular would be not, and don't worry about CD. You don't have to worry about that. Lenticular, also, it's just kind of in there. Anybody remember lenticular? A spiral with no visible arms, right? So actually, according to Hubble, that would have been the first stage of a spiral galaxy. It just hasn't formed arms yet. So the Hubble tuning fork is something you're supposed to be aware of. It's on your final exam. And in a few minutes, when I get to the advanced questions, you're going to see there's a question on the tuning fork. And in particular, Hubble's tuning fork. Why don't we draw it real quick? Actually, why don't I just put it up? I'll put it up for you. That makes more sense. Hubble tuning fork, right? So the Hubble tuning fork was right here. There it is, Hubble tuning fork. So Hubble thought that conservation of angular momentum, an elliptical galaxy was a galaxy that had not formed a disk yet. It was a big cloud that is going to collapse, right? So this was the earliest galaxy. And these ones are the latest forms of the galaxy. So an elliptical, this is what Hubble thought. It's on your final. What did Hubble think? He thought that ellipticals evolved into spirals, right? And so you can see the numbers are getting bigger because it starts off as a spherical distribution. And then as it collapses, it rotates faster and flattens, right? So it's getting more elongated. And he said that this picture is real edge on, not edge on, face on. You're seeing the whole circle of a spiral galaxy with no arms, right? There's no arms there. That would be lenticular. No obvious arms there. Then he had two branches. One turns into a spiral, regular spiral, and the other where it turns into a barred spiral. So in Hubble's mind, the galaxies became sharper and sharper in the definition of the arm. That was what he did. So he gave them letters to show the sharpness. And so the most well-defined arms were the end ones here. Okay, so was he correct? He was not at all correct. He was completely backwards, but it's not his fault. He just didn't have enough information. So one of the things that we've learned about is that elliptical galaxies exhibit a few traits that you know about that Hubble did not, right? So number one, what is the number one thing that you're supposed to know about elliptical galaxies? They have no new stars, right? So when you look at them, astronomers don't see any blue, right? There's no blue, there's no young stars. there are only old stars. So they look reddish, right? They have a red tint to them because there's a lot of older low mass stars. So the Hubble tuning fork we mentioned is the evolution of galaxies. So Hubble thought that ellipticals turn into spirals. In fact, we will learn in a little while that it's the opposite. Okay, so what's a megaparsec? Need to know what a megaparsec is. There is a question on your final exam that asks about something with megaparsecs. You need to know what it is. What's a megaparsec? A million parsecs, right? And a parsec, you're supposed to memorize at some point, is 3.26 light years. So it would be 3.26 million light years would be another way to say megaparsec. Mega is the metric prefix for million, okay? Edwin Hubble, why is he important? Well, boy, the name is just sitting there, but does anybody know why it's there? What's going on right now? We're still talking about this debate, right? The nature of the universe. Is the Milky Way everything? Or are those spiral nebula other galaxies? And the right answer was spiral nebular galaxies. So there's two people here. Oh, Heber. I didn't put his name up there. Heber and Shapley. I say Heber. Curtis and Shapley are the two debaters. So you're supposed to know who's who, right? Who was Harlow Shapley? He was the one who found the center of the Milky Way by using globular clusters. He thought that the spiral nebula were part of the Milky Way. He was a fan of this being everything. This is it. Everything we see, that's it. That's the whole universe. And Heber actually was a much bigger idea, right? He said that those little things are other galaxies. And therefore, we are just an island in the middle of the universe, right? We are one galaxy, a little island, and those are other islands, right? And there's vast spaces between them. He turns out to be correct. So who was the one who settled the great debate? Hubble, Edwin Hubble. And you're supposed to know how he did that. So it looks like I jumped right out of that. It's coming up. But Edwin Hubble is famous because he observed the Andromeda Galaxy, and it's going to come down here. How did he finally settle the debate? He measured the distance to the Andromeda Galaxy. How did he measure it so well, and why did it settle the debate? What do you remember? So he measured the distance by using Cepheid variable stars, right? These are stars that pulsate in brightness over time, and the longer the period, the greater the luminosity of these stars. So by measuring the period, he could watch how long they take to do their oscillation. He knew their luminosity, and if you know the luminosity, what can you use the luminosity to find? The absolute magnitude, right? You remember this? Okay. If you know the luminosity, you can find the absolute magnitude. Compare it to what you see, the apparent magnitude. And when you compare those two, they're not the same number. You can calculate the distance. Cepheid variables to measure the distance to Andromeda. So the way the Cepheid variables work is the longer the period of the variable star, the greater its luminosity. So there was a relationship. We can bring that up. Should we bring it up? That's Henrietta Swan Leavitt. Oh. Henrietta. Our lovely Henrietta. Here we go. Henrietta. Well, let me just put Cepheid variable. Wikipedia, of course. The best. Love you, Wikipedia. If you haven't donated lately, donate. Okay. Oh, come on. Where's the period? Okay, maybe we have to go to Henrietta. Okay, here we go. Henrietta. There she is. All right, there she is. We don't want to. Okay, I guess all we got is that. Okay. It's a little. Okay, there's two versions. This is. I'm not sure why. Why are there two? But anyways, this is a little more complicated. This is the actual paper, so legit data. But she showed that the longer the period, the greater the luminosity of the star would be. So our discussion was with the Cepheid variables was that the greater the luminosity, Well, the luminosity tells you the absolute magnitude. If you know the absolute magnitude and you can see its the brightness, the apparent magnitude, you can compare those two and calculate the distance. Okay, so I guess I could have brought up the slides, right? I had it right here. I forgot. Right here. Okay, that's it. I forgot it was on the slides. Okay, so that's the idea. So the longer the period, the greater the luminosity. Okay, Cepheid variable. All right. So, okay, so, all right. A lot of words. Calibration. What's calibration mean? I feel like I should just start talking about the other things. What's calibration? So we have a number of techniques for measuring distance, but they're not independent. They depend on each other. They are not independent. They depend on each other. So each step in this cosmic distance ladder, we call it, is going to require the steps that came before. So the new technique that you're going to have is going to be calibrated to the previous technique. There must be a star or object that you can use both techniques with, the old technique and now the new technique. And when you do that, you want to get the same answer. So we have to calibrate the new technique. So calibration is the way we set the new technique's distance scale, right? That's kind of what's going on. So maybe I should just jump to the ladder. Should I just jump to the ladder? So we've got a number of different techniques, and you need to know them in order. And there's not a lot of that you need to know otherwise. Maybe just a little bit of how they work, but not much. Okay, so the cosmic distance ladder is the idea that we need a number of techniques to get to the furthest distance in the universe. The first technique that we start with is parallax, right? That's good for seeing little shifts in the positions of stars, and you guys know how that works, but only for the nearest stars, about 1,000 parsecs away. Within 1,000 parsecs, we can see parallax. The next technique is called spectroscopic parallax. We'll just list them, right? And that one uses spectra. It is not, in fact, parallax at all. It doesn't use parallax. It uses spectra, but it measures distance, and so the name parallax was given to it. Cepheid variables, that's the one we just mentioned. Henrietta Swan Leavitt invented it, and then Edwin Hubble really made use of it to measure the distance to the Andromeda Galaxy. There's Tully-Fisher, which is the rotation curves of galaxies. Their magnitude or absolute magnitude luminosities should be determined by the rotation velocity. It's not a very good technique. You don't actually have to know that it's not that good, but it sits between Cepheid variables and type 1a supernova. What's a type 1a supernova? A white dwarf with a companion star. What kind of companion star? A red giant. Red giant is feeding the white dwarf, and every time the white dwarf gains a little bit of matter, what happens? You get remember the flash, what's it called? A nova, where you get a nova. And then the white dwarf gets a little bit more massive. But one day, what happens? Goes above the limit. There's a limit. White dwarfs can only be the Chandrasekhar limit, 1.4 solar masses. Hopefully you didn't forget that number. And at the day that it goes over that limit, the whole thing collapses and instant, runaway fusion event. All of that carbon and oxygen that was in the white dwarf explodes in a type 1a supernova. So do we know the mass of a type 1a supernova? 1.4 solar masses. We know that that's what happens. It goes off when it hits that limit. And so we know the luminosity and the absolute magnitude of it, which means when we see them go off, we can compare them to the absolute magnitude and we can figure out the distance. It's an excellent standard candle, right? Remember that idea, excellent candle. And finally, we get the last one is called Hubble's Law. What does Hubble's Law say? That galaxies that are not in our local group are all moving away from us. And the speed that they are moving away from us depends on how far away they are. The further away they are, the faster they're moving away from us. So that constant is called the Hubble Constant. Why don't we just quickly go through these again with the slides? How about that? Good idea? Okay, all right, here we go. Go back to the PowerPoint, okay. Okay, so here's the ladder in order, right? The closest one And it's good to about 1,000 parsecs. You don't really have to know these numbers. Just you want to get the idea. Each technique takes you further away from our solar system, right? So after this one, 10,000 parsecs, are you outside the Milky Way? Are you outside of the Milky Way right here? 10,000 parsecs? How many parsecs is the Milky Way? 30,000 parsecs. So we're not even outside of the Milky Way. You need this technique to get outside the Milky Way. The Cepheid variable was the way that Edwin Hubble finally measured the distance to the Andromeda Galaxy. So to get outside of the Milky Way, you can't get out until you finally get to this third technique, right? This finally lets us measure the distance to like Andromeda. I forgot to mention, do you guys, it's in our discussion coming up. Does anybody remember the distance to the Andromeda Galaxy that Edwin Hubble got? Well, that's what the real number is. That's good. He got about 1 million. But either way, 1 million is huge. So 2.5 million light years, 2.5 million light years, 2.5 million light years is the real distance to the Andromeda Galaxy, right? And so it's millions, not thousands, right? Not hundreds of thousands. So it's just much further away. It has to be outside of the Milky Way. Yeah.
What's the difference between the Hubble constant?
The Hubble constant is inside of the Hubble law. It's the constant of proportionality. So in order to use the formula, we need to know that constant value. Let me mention that in just a minute if you can, okay? What's that?
Did you mention it?
No, I haven't mentioned it. I will, though, in a couple minutes, right? Okay. So number one is parallax, right? We know how it works. Take a picture of a star. And then when do you take the next picture? 6 months later, when we're on the other side of our orbit. And that gives us the biggest separation between our two positions. The larger the separation distance, the better the precision of your measurement. So you want them to be as far apart as possible. They could be done close, by the way, but you're not going to get the precision. So this is the best we can do from Earth, a baseline of 2 AUs. We should remember that, right? There are review questions on there too, right? I don't know if that's one of them. Is that one of them? I don't know. Okay, the next one is called spectroscopic parallax. Again, you don't have to know a lot, but you should understand the idea. The idea says that if two stars have the same spectra, that they are virtually twin stars. And by twin, I mean they have the same mass, luminosity, and absolute magnitude, right? They have the same absolute magnitude. So if you know one of the stars, right, and you compare it to another star with the same spectrum, then you can say that's a twin star, but look it's a lot dimmer, right? Its apparent magnitude is very small compared to this one, but I can calculate the distance using that information, okay? So you get the idea? Two twin stars, you can, if you know the distance to one, you can calculate the distance to the other one, okay? You're counting on them being twins because they have the same set of colors. They are the same surface temperature. They are the same mass. They're the same spectral classification. Okay, Cepheid variables, we know how that works, right? Longer period, greater luminosity. That one's good out to millions of parsecs, which gets you to other galaxies, right? And then here we did that one. Here we go, Tully-Fisher, ugly one, but you know. A galaxy's rotation on the edge of the galaxy, the speed of the stars rotating, speed of the stars orbiting that galaxy should depend on the mass of the galaxy. Sorry, question, yeah, Duran. No, we don't do math in this class. If you want to do the math, come take that astrophysics class. Sorry, just want to mention that. You know, we do the math in that class, but not in this class. No formulas needed. You can just look at them and go, ooh, formula, you know, but we don't do it. No formula. Okay, this one is very, very difficult because there's a lot of assumptions that you have to make. But the speed of a star orbiting a galaxy is dependent on the mass of the galaxy. More mass of the galaxy, the faster the star will orbit. And from this, they estimate the luminosity and the absolute magnitude of the galaxy. Okay, so that's how they do it. It's not very good, like more than 50% error sometimes. So you kind of like, why are you doing it? but you don't have any other choice maybe. It's the only good technique. There's no type 1a supernovas going off, but you can measure the rotation curve. So you use what you can, right? You do the best you can. All right, and then after that comes type 1a supernovas, okay? Type 1a supernovas, white dwarfs, exceed the Chandrasekhar limit, they blow up, and we know what their luminosity should be and their absolute magnitude should be. They were really important. And finally, we get to the Hubble Law, which says that the further away something is, a galaxy is, the faster it will appear to be receding. So this h here is called the Hubble Constant. So d is the distance, and v is the speed that the galaxy is receding. So let me take a moment and break away and make sure you know how to use this, because there's a question on your final which is related to the Hubble Law, which you might have anticipated because it's kind of a big deal. How far away does the Hubble, whoa, am I running out of battery? Can you guys hear me? Okay, why is chapter 17 and not part of the study guide? I made a mistake, chapter 17, hi, is not on there, okay? Somebody waved, right, so. Okay, we're down to 4 people now though, right? I guess other people had other things to do. Okay, can you guys hear me okay? Okay, yes, okay, good, good. All right, let's take a look. All right, let me. Okay, how do you use Hubble's law to calculate? Actually, you're not going to need to do any calculation. Sorry, what are we going to use it for? Very, very simple. Okay. So we don't do math, but, you know, Hubble's law is a tiny little equation. So the speed of a galaxy is the Hubble constant times the distance, right? How far away is that galaxy from us? So here's our Milky Way, right? And there's a galaxy over here, a certain distance d. And that galaxy is moving away from us with some velocity. What if we go in a different direction, right? But we go twice as far away, right? It doesn't matter which direction you go. If you go twice as far away, how fast is that galaxy receding from us? And the answer is, if you go twice as far, the speed is going to be twice as fast, right? So that's the idea. It's going to be going 2v, 2 times whatever v was, right? So that's the idea. That's about as hard as it gets. If you go 3 times as far, 3 times as fast. That's the kind of thing you're looking for. Now the equation, actually you're supposed to know the current value of the Hubble constant. Did I tell you guys about the problem? I probably mentioned it, didn't I? No? Okay, take the black holes class or the astrophysics class, we'll talk more about this. But the best number right now is 68 kilometers per second per megaparsec, right? So how does this work? If you measure the distance has to be measured in megaparsecs, right? So the distances to galaxies are really big, right? Remember how big, how many megaparsecs? It's less than, so 2.5 million light years is less than 1 megaparsec, right? So Andromeda is actually less than 1 megaparsec from our Milky Way. But most of the galaxies we're going to worry about are much further away, 10, 100, a billion megaparsecs from us. And so you put that number in, multiply times the Hubble constant, and you get the speed. What is the speed going to be measured in? You guys figure that out? So if you multiply this thing by megaparsec, right, let's say 10, right, then the megaparsec cancels. Okay, and what do you get the speed measured in? In kilometers per second, right? So the speed is going to be, in this case, 680 kilometers per second. We're not doing math, though. We don't do math, okay? But the further away you go, the faster it is receding from us. So, yeah. Okay, let me ask you a question. How did they measure the galaxies were moving away from us? You need to know that. I don't know if we talked about it in class either. How do you know? What happens to the light of the galaxies that is moving away from us? It is red shifted. Thank you very much. That's right. And the further away they are, the greater the redshift is. Do you understand it? That's how they actually measured it. And then they created this formula. So I don't want to tell you that there are galaxies moving faster than the speed of light away from us right now. I don't want to tell you that, but I mentioned it. You don't have to know that. That's actually beyond your class. Okay. Did we cover that? Hubble's law, Hubble's constant, you got it? Okay, cool. All right, so we are now in the last section of the chapter, which I didn't cover very well. So make sure you're paying attention. There's some questions on the final that are related to this. Active galactic nuclei is a catch-all for any galaxy that shows activity, right? Actually, not just the galaxy, the core of the galaxy, the nucleus of the galaxy. So active galactic nuclei is the term that we describe, which is a beautiful framework which explains some mysteries that we've had up until now. Now we can explain all of them with one model, right? So active galactic nuclei is a model to show why some galaxies look like this and other galaxies look like this, right? And so we'll talk a little bit about what they might be, right? So the first example, so active galactic is any kind of galaxy that shows activity coming from its core, from its nucleus, active galactic nuclei. Is the Milky Way have an active galactic nuclei right now? Not right now, and most of the time the answer is no, but last year it did flare up, and there was gamma ray bursts coming out of the core of the Milky Way. So it was active for just a little while. It is not active right at this moment. And up until now, it's been totally quiet, right? We have not, for the last 30 years, Milky Way, quiet, quiet, quiet. It's quiescent. But then it flashed last year. It ate something, right? So we'll talk about that. Okay, so there's a first galaxy. It's called a Seyfert Galaxy. And I put in the notes, you had to know type 1 and type 2. It's not a huge deal. A small deal, but a Seyfert type 1, actually, you know what? I think it's probably easier just to go to here, to Wikipedia, right? And they mentioned the two Seyferts. Seyfert. So we saw Seyfert Galaxies. They were streaming Seyfert Galaxy. Here we go. Seyfert Galaxy, don't scroll away. I already paid you, I gave you money. Are one of the two largest groups of active galaxies, along with quasars, right? They have quasar-like nuclei, very luminous, distant, bright, blah, blah, blah. Okay. Seyfert galaxies account for 10% of all galaxies. Okay, so, but there's two types. Seyfert type, okay, there's actually more, but we don't worry about that. Type 1, Seyfert galaxies are very bright sources of ultraviolet, X-ray, and what? I thought it was radio waves. Hey, what do I know? Your book says radio waves. Wow.
You can't always trust Wikipedia.
All right. Okay. Actually, they were not. Okay, so actually, I have to ignore Wikipedia for a minute. No, it's not wrong. It's just the first discovery of these galaxies was with radio astronomy. Okay, so in your notes, just bear with me. This is historic. We're kind of talking about 30 years ago when we first started looking with radio telescopes. We found these galaxies that had bright radio emissions coming out of them. Seyfert type 1 is a bright radio source. Okay, so that's what you want to know. Seyfert type 1. Seyfert type 2 is a bright infrared source. So instead of radio waves coming out of it, we don't see a lot of radio waves. We do see very bright infrared coming out of it. Lots and lots of infrared coming out of it. So Seyfert type 1, Seyfert type 2. Got it? Okay. And then we have another thing you're supposed to know about called a quasar. You're supposed to know the quasar. What does quasar stand for? Quasi-stellar, anybody remember? Quasi-stellar radio source, okay? But these were incredibly powerful. In fact, they were so powerful, this is the part that I want you to know, we could not explain how that much energy could come out of a galactic nucleus. We could not explain it. There was no physics to explain that much energy coming out. And the reason why, it's really cool to understand why it was so hard to figure out, because they made a mistake in understanding what quasars were. They thought that the light of the quasar was shining in every direction, and it wasn't at all. What was the quasar actually? It was one of the jets shooting out of the active galactic nuclei. So it's like saying you've got a light bulb which shines in every direction, or you have a laser. Are they the same thing? No, right? But if you had a light bulb that shines lasers out of it, it would be incredibly powerful, like super dangerous, right? It would be so dangerous. Laser beams coming out of every direction, right? And so they made a mistake in estimating how much energy. And the reason was it was just coming out of jets, not in every direction. Does that make sense? You got that? Okay. So quasars are also explainable by the active galactic nuclei, unified active galactic nuclei. Okay. So superluminal. Anybody know what superluminal means? Super, above, luminal, the speed of light. We see jets coming out of these galaxies going faster than the speed of light. Is that possible? It's not supposed to be possible. And it turns out it's not. It's not real. It's a manifestation of the jets coming almost straight out at us. And so we don't measure properly. There's something, not quite right, but they're near the speed of light. They're so close to the speed of light that we can make that kind of mistake. So you want to be aware that some people have measured jets moving faster than the speed of light, but every single time they've gone back and fixed their numbers, they realize they're not quite moving faster than the speed of light, but very close to the speed of light. But the word superluminal means faster than the speed of light. Should not be allowed. Okay, and we have our unified model. We want to talk about our unified model, and our unified model is going to explain all of these different galaxies. And what it really is about is which direction are you looking at the galaxy from? And using this unified model, we can see all of the galaxies that we've mentioned, the Seyferts, the quasars, and another called a blazar, which is again like a quasar. Okay, so let's draw a picture. That's what you should be able to do. Draw a picture of a unified active galactic nuclei. Here we go. There's our picture. So for those of you at home, there's a few elements that you want to know about. What's at the center of this active galactic nuclei? The center of it? A supermassive black hole. Right? That's the power source. The supermassive black hole is going to make everything happen. So you got the supermassive black hole at the center, and around it, if it's active, there must be an accretion disk. Remember we said that our Milky Way is not active right now? The reason is it's not feeding on anything. In order to be active, you need to have an accretion disk. So active galactic nuclei have accretion disks around them. The next element to try to help us understand how this works is around the accretion disk is a big donut of dust called the dust torus. And lastly, the thing that happens because you have an accretion disk, you're going to have hot charged matter circulating, and from that you're going to generate a very powerful charged matter circulating. Anybody know what I'm talking about? Charged matter, magnetic field. Because of your powerful magnetic field, you're going to get twin jets, one out of the North Pole and one out of the South Pole. The jets come from a magnetic field phenomenon, right? How does it work exactly? I don't know, but I know it's magnetic field, conservation of angular momentum. These ideas must be the right answer, okay? And they also can give you some amazing speeds when you do it right. Okay, so how do you get the different types of galaxies? So Seyfert type 1, you're able to look all the way to the core where the radiation is coming out. All kinds of radiation, not the direct jets, but the radio waves that are coming from the accretion disk area. If you looked in the visible or the X-ray, you would also see light there. But in the early astronomy, they didn't have all of these cameras. They had radio telescopes, they had visible light telescopes. They just didn't have access to all that information. So the original Seyfert type 1 saw the powerful radio signals coming all the way from the core. Seyfert type 2, you're looking along the plane of the active galactic nuclei, right? At the torus. So you're looking at the dust, which obscures the direct radio wave. But you can see infrared radiation because of that light passing through the infrared. So you should remember that infrared light passes through dust, right? That's one of the things that we can see through dust with the infrared light. And then the last one is if you're right along a jet, what do you see? you're seeing that huge amount of energy. You're seeing a quasar, or a blazar is another name. Okay, don't worry about that. So actually, I like quasar, but blazar is another word, another term for it too. Okay, any questions about that? So you got it. The universal unified model has, what are the elements one more time? Supermassive black hole, accretion disk, torus, and jets. Okay. All right. Okay. So what's an outflow coming from? Where do the outflows come from? We've talked about outflows before, from the jets, right? The jets cause the outflows. Okay. Here we go. We're almost done. This is so early. I told you we're going to be almost done. We're going to be done early. Describe the nature of the Great Debate. What was the Great Debate? The idea is, how big is the universe, right? Is this everything? The Milky Way is everything? Are the spiral nebula inside the Milky Way, are they just like planetary nebula? Or are they far away, and are they full-fledged galaxies? So Heber and Harlow, which one was Harlow? Harlow was a small guy or a big guy? Which one? Small. He thought the Milky Way was everything. And Heber Curtis thought that those spiral nebula were other galaxies. He turned out to be the right one. Okay. Describe the difference between spiral and elliptical galaxies in terms of morphology. Ooh, that's a really good word. And also the rate of star formation. I think maybe the reason that word's in there is because it's in the title of my dissertation. So just for fun. So maybe you can learn the word morphology if you haven't heard that word before. Anybody know what morph means? It means form. It means shape. Morphology refers to the form and the shape of these galaxies, right? So what do you know about elliptical galaxies? Are they kind of round or kind of flat? Which one? Kind of round, right? Either spherical or more oblong. Elliptical galaxies are roundish, right? Whereas spiral galaxies are really flat. They have that flat planar structure. All the stars are going the same direction in a spiral galaxy. What about elliptical galaxies? No, they're going in all different directions, right? There's very, very little organization there. So major differences in terms of morphology and rate of star formation. Where do you get new stars? In spiral galaxies, lots of new stars. What part of the galaxy do the new stars form? In the disk, where all the fresh matter is located. So dark matter doesn't seem to make stars. That's not relevant to your class, but it's interesting to me. You know, it's something you should think about. Dark matter doesn't make stars. So somehow it's not going to be good stuff for stars, right? Not stars. Anyways, rate of star formation. So elliptical galaxies, no new stars, right? That's kind of a cool thing there. And how did Hubble originally interpret the tuning fork? He said ellipticals evolve into spirals. In fact, we now know the other way around, right? Spirals collide and merge, and if they don't have the same angular momentum, that when they mix together, they make a big mess, which will be the elliptical galaxies. Another little clue was the number of globular clusters. Which one has more? Spiral or elliptical galaxies have more globular clusters? Ellipticals have more, which again works, right? If you merge spiral galaxies, then you merge and put together the globular clusters. You get more. That makes sense? Right? Okay. Describe the major components of the AGN, unified AGN. What are they? Supermassive black hole, accretion disk, dust torus, and jets. There you go. Okay, 1/3 of the spiral galaxies are barred. I don't know why you need to memorize that. I don't know. I guess I put it there. Can you remember that? Not all of them, 1/3. Okay. What are the rungs? Should we go through that real quick? What are the rungs? Closest rung. Parallax. Okay, the next one has the word parallax in it, but it's not. Spectroscopic parallax. The third technique finally gets you out of the Milky Way. Edwin Hubble, Cepheid variables. Very good. This one I don't like very much. Tully Fisher. Okay, this one's awesome, and it's a supernova that comes from an exploding white dwarf, type 1a. And the last one, galaxies are receding, the Hubble Law. Good for you guys. Anybody got that? You got that memorized already? Okay, you need to know them in order by the time you get there. And the current value is not right. Oh, it's not right. 68. Oops. I made a mistake. It's 68 right now. Sorry about that. 68, not 69. That was a couple years ago. Huh?
I think it says 79.
And which one?
Wikipedia 70.
Right now? I don't want to tell you. Wikipedia tells 2 numbers. Yeah.
Looked it up.
Okay, you just looked it up. Did you find 74
No, we found
and 68? I think are the 2 numbers.
Change the Wikipedia.
I didn't want to confuse you, but thank you for checking me. That's awesome. I love that you would do that. Okay, so here is the current value. Okay, so 68 is the current value using this technique. But there is another one that's 74, and they are not, they don't agree with each other. And so the answer is, what the F is going on? We have a big problem. We actually have a big problem. We do not know what's going on. So, but actually there's a solution. And actually, I think I told, anybody miss class on Thursday? Raise your hand, I missed class. Because there's a secret question. But everybody here or listening to the video is going to find out. Oh, well. That's okay. I actually want you to know about it. Anybody want to know? Nobody wants to know? If you already in the class, you already know the secret question. The secret question says, it seems to be that the Hubble constant is not a constant. Okay. So this constant that we kind of wanted to be a constant actually lets us go backwards in time and say that there was a big bang X number of years ago. By the way, I will predict that in the next couple of years, you're going to hear a revision on how old the universe is. Okay, I actually know. First of all, it's not a prediction. I know that because they are revising the Hubble constant, they will then revise the age of the universe. Does everybody understand me? Okay. So the age of the universe is based on the current value of the Hubble constant. When we change it, we change the age of the universe. Okay. It's not that the universe has a certain age. The problem is the technique we use for measuring it is getting better, or maybe not, right? Because I just told you we have a second value that doesn't match the first value. And that's a problem. Except, maybe not. Maybe it's just telling us that the Hubble constant is not a constant. That the universe is expanding, but the rate of expansion is changing. And so everyone here needs to know that the rate of expansion is getting faster. Okay? Now, again, we don't talk about it in our class, but there is an explanation, and it may be the right answer. But Albert Einstein came up with something called the general relativity field equations. And he made a guess about the nature of space-time. He said that the energy of the universe is constant. But when he made that law in the first place in 1918, he thought that the universe was static and unchanging. And then he found out that the universe was expanding. He was like, uh-oh, oops. He considered it to be one of the biggest mistakes he ever made. And he took the constant out of his equation. But we put it back into the equation because we think that he was right. So the idea is, very simple idea, that the energy of the universe, if the universe is expanding, the density of energy should be getting bigger, smaller, or staying the same. If it's expanding universe, you might expect the energy to be spread out more. So the energy density would get smaller, right? That's what you would expect. But Einstein put in his equation that it should be constant. And it does, in fact, seem to be constant. Something's wrong. How can it not get less? How can it stay constant? The answer is there is something called dark energy that is coming into our universe. From where? How? I don't know. But the impact of this dark energy is to accelerate the expansion of space-time. So if I ask you the question, what is the impact of dark energy on the expansion of the universe? The answer is, it is causing it to accelerate. The expansion of the universe is getting faster over time. This is scary, and I don't know why, but it's interesting. One of the answers might be, and if you find this intriguing, there's a course called Black Holes in the Universe where we talk about this. There may be other dimensions that we can't see. There may be other dimensions, or it may be coming from another universe entirely. There may be other universes, okay? It's just something to be open to, I guess, because we can't explain where this dark energy is coming from, okay? So at this point, I am done with the review, and I will do the 10 questions if you want to sit here and watch that. Otherwise, you guys are free to go. But if you haven't seen the 10 advanced questions, I'm going to do those right now. Thank you very much. Good luck. I hope you guys get a chance to look at your old exams as well. If you didn't sign the attendance sheet, please sign the attendance sheet. Okay, for those of you who are staying, here are the preview questions. You're welcome. See you later. Yeah, no problem. Thank you. Okay, question number 1. If you haven't seen these before, this will be on the final. These are 10 questions on the final. Question number 1. Which of the 4 fundamental forces of nature do we believe dark matter that dark matter interacts with ordinary matter? So we know gravity, but it's probably not the strong nuclear force. And it's definitely not electromagnetism. The only other possibility is the weak nuclear force. So the right answer is D, gravity and the weak nuclear force. And we don't know that for sure, but we're hoping that that's the case. Yeah. Yes, the ones that are right out here are open, yes. Okay, the figure below shows our tuning fork. Everybody remember the tuning fork? At which labeled point would Hubble have placed an elliptical galaxy? And the answer is he thought it was the beginning of the whole thing, right? It just had to collapse and turn into a disk galaxy. So D is where Hubble would have put the elliptical galaxy. Okay? Everybody good? Okay. Question number 3. An astronomer measures galaxy A. I'm giving you this question. Oh my God. Okay, so this is the Hubble's law. This is actually where it's relevant. To have an apparent recessional velocity of 1,000 kilometers per second. Galaxy B is twice as far. How fast is it receding from us? And the answer is twice as far, twice as fast. So 1,000 times 2 is 2,000 kilometers per second, right? Twice as far, twice as fast. Great, question number 4. Oh, I changed this answer, shoot. Okay, but you know the right answer. There may be 5 answers on your final. I put another answer, I forgot. That's not fair, is it? Oh well, live with it. I put indigo in there, but it's wrong anyways, so. Just another distractor. I wanted 5 for some reason. I don't know why. Okay, which color is emitted most strongly by the sun? The center of the light curve from the sun. What color is it? Green, right? The beautiful green color. 504. It doesn't matter about the 504. Green is the color of our sun, right? The center of our sun. Roy G. Biv, right? Roy G. Biv. All right, here we go. When an exoplanet, old question, right? When an exoplanet passes in front of its star, the light of that star dims for a short while before returning to normal. This is called the what method? The transit method. The transit method. Okay, transit method is like looking at the light curve of a star, seeing it dim. Okay, which of the following situations has the greatest variation in tide? The highest high tide, this is a really old question, exam 1. The highest high and the lowest low. So what causes the tides on Earth? The moon and the sun, both of them, right? Moon is more important, but the sun is also important. So what happens is you get the highest high and the lowest low when they work together. What phase is the moon when they work together? Either a new moon or a full moon. What is it called? Spring tide, right? So is it neap tide? No, it is definitely not. Is it a first quarter or a third quarter? Definitely not. Is it a spring tide? Yes. Is it A, B, and C? No, those are all wrong, right? So the answer was spring tide. When the sun and the moon line up with each other, either as a new moon or a full moon. Okay. Oh, we've seen that question before. Oh, you just had this question. Last test. From the data given with a double second comma. I got to get rid of that second comma. Okay. Which star in the table has the greatest surface temperature? O, B, A, fine, girl or guy, and Kiss me, right? So you just do it in order. The hottest is an O. Any O's up there? So you got to look at the spectral class. Any O's? No O's. What's the next letter? B. There's a B. That's the next hottest star. What would be the third hottest? Well, I don't know, right? I don't know. It's an A74, but you don't know that yet. Okay, but it doesn't matter because B was the right answer. That was star HR 4621. Okay, HR 4621. Letter C in this, it's probably going to be mixed. Yeah. O is the hottest. O, B, A, fine girl, kiss me. What's the coolest? The M's are the coolest. Yeah, that's right. That's why you memorized it. So you would know the letter from hottest to coolest. What was the subject of the great debate? Oh man, I can't believe I gave you this, but this was really bad. The last time I gave this test, 30% of the students got it right. I don't know why. It's such an easy answer, but 70% of the class got this wrong. How is that right? Anyways, what is the nature of the great debate? The great debate, settled by Edwin Hubble. The age of the universe? No. The truth of the geocentric and heliocentric? No. The truth of the Big Bang? No. Didn't know about that yet. The nature of spiral nebulae. Are they inside the Milky Way or are they separate galaxies, right? And we finally found out that they were actually different galaxies. Everybody good? Spiral nebulae. Okay. You observe a lunar eclipse. Oh my gosh. Exam 1 again. You observe a lunar eclipse. What phase is the moon during a lunar eclipse? It is full. It's passing into the shadow of the Earth. Full moon, right? The figure below shows a binary star system. The stars are orbiting each other, and we see them moving because of their Doppler shift, right? So which star has a blue shift, A or B? Which star? B is coming towards us. That's the blue shift, higher frequency. And the A is moving away. That's a red shift. Which one's moving faster, the smaller mass or the larger mass? The smaller mass has to move on a bigger orbit. It moves faster. And so you get a large red shift for A and a small blue shift for B, right? So which answer is that? Star A has a larger red shift, okay? The answer order may be wrong, right? Don't pick the letter, pick the answer. Everybody good, right? Oh, that's it. Thank you very much. You're going to do great. Take some cookies. Oh, can we have a piece of cake? Yes, we got cake. Check it out. Sorry, people at home, there's no cake for you. I know, new record. Yes, it's a new record. It is a new record. Thank you very much. Thank you very much. All right, good, good, good. All right, we're ending our stream. Thank you. Thank you, Liz. See you later. Shout out. Yo, shout out to my people. Yo. Okay, here we go.